Um, yeah, I'm Tess. I'm a data scientist, a software engineer at Microsoft. How many in here are data scientists? Awesome. It's so great to actually be talking to a bunch of people who actually know what I'm doing. Because usually I get to talk at conferences where people go, machine learning, something in the future. I have to say, I'm a software engineer first. I like to create good software, but sometimes solvable by data science and machine learning. But I don't like to go into the room sort of like machine learning first. I think we should apply machine learning where it fits. And one of the places where it does fit is what I'm going to talk about right now in video action detection. So video action detection is an area that you can definitely not do without machine learning. So video action detection, does anyone work with that? Very few. It's quite a new field, actually, in deep learning. So what you can use it for is things like, if you look at a movie, trying to figure out what rating it should have based on how much blood and gore there is in it and things like that. Or detecting actions like someone shopping or someone shoplifting in a store, or maybe crashes in a Formula 1 game to create like watch videos. And specifically, I'm going to talk about a project that we've been working on in my team, that's soccer action detection. So we bring in a video, a soccer match, and then out comes a highlight reel. And the question is, how the heck do you do that? So one way, the way they solve it right now is sort of like they take a video that comes in, they have manually created markers, so people who actually sit down and create events saying basically there is a shot on goal, there is a red card or yellow card or something like that, or an injury. And then we have some kind of expert system. After that, it takes like all these markers and says, these look like interesting ones. And by expert system, I really just mean, some logic code that takes all the goals and some of the shots on goal and maybe the red and yellow cards. And out comes a list of clips that could be good highlights and put together in a video. Now, one way we could solve this with machine learning, so one of the problems with this is that the events that they're gathered are very expensive to gather. Like having a human actually mark down everything, it's not possible for every single game in the world. It's possible for sort of like the high-end UEFA games, but not necessarily for your kid's soccer game or for other leagues. And also we use markers from IoT devices, so things like GPS sensor and IR sensors on the arenas, but that's also not available on smaller leagues. So one way to solve this, sort of like to remove the human's need to create all these markers, is to do an end-to-end solution where we have a match video come in and a highlight video come out and create a model in between. But if you're doing any machine learning, you know that in order to create such a model, you would have to have a lot of videos, a lot of highlight videos, and then sort of train a model to figure out the matching between the input and the output. And in this case, that turns out to be extremely hard because the input videos are 45 to 48, maybe 49 minutes, depending on how long the overtime was, times the number of frames per second, and every frame has a large number of pixels, like height and width. So there is a huge amount of input, and the output is also a video, and the video is, somewhat arbitrary. Someone put together a highlight video, and they may or may not have taken like all the shots on goal and all the goals and everything. So it becomes a very difficult task to have an end-to-end model where you have input and output like that. So instead, we go through and we sort of cut down the problem into smaller pieces. So looking at the original system that they had, we went through and said, what if we just remove this part and replace all the markings with different models? So one model that would take the red cards or the shots on goal, and maybe one model that would take the injuries. So we create these models for the markers. So that now becomes a very much smaller task, and that's what I'm going to show you how to do today. So we're going to focus on the model that does the shots on goal. Now, it's still very tricky. Like, how the heck do we go through and figure out if someone is shooting on goal? So the way we went through this was like this. We looked at the markers that we had, so we take that as input data, and then we create 5-second clips around all the markers. So every time someone has said there was a shot on goal, we cut out a 5-second clip right around that mark. 5 seconds is kind of arbitrary, but the reason we picked 5 seconds was because we didn't know if the markings were going to be super exact, so we wanted to make sure we actually captured at least the shots on goal. So these 5-second clips are now listed as being sort of like one event. And then if we're going to detect shots on goal, we need to figure out what's not a shot on goal. So if you're going to do any kind of classification, let's say you're going to do image classification on finding cats in pictures, you have to figure out what you're going to use as not a cat to train the model with, right? So if you train the model with just white screens, then it will only learn that a white screen is not a cat. It won't learn very much about what a cat is. Or if you train it with dogs, it will probably learn a lot better because dogs and cats are very similar. So you want to make this line in between very narrow. So the negative sampling in this case is trying to figure out what can we use that's not a shot on goal, but it's very similar. So we don't just get clips that have like panning in the audience type thing. And for this, we chose attacks. So attacks where someone was shooting on the ball, but was not really shooting in the direction of the goal. The next step in this process is now we've decided sort of what we're going to try to figure out, but now we go through and do some kind of data survey where we figure out and look at the data and see, do we have any telltale signs, some things that allows us to understand as humans what makes a shot on goal. So a couple of the things that we looked at was audio. And you can think of it as if you're listening to a football game, you're probably very likely to even hear whether or not there is an interesting event going on, right? So audio turned out to be a very useful feature to look at. So now we're looking at what we can use as input features. And the other one that we theorized around was the speed and direction of the players, because the speed and direction of the players seemed to be very interesting in terms of figuring out if they were shooting on goal or not. And whether or not players were grouped, because we saw that when people were shooting on goal, we had like a number of people around the ball and then maybe some defenders and things like that that could be used as input features. And whether or not the goal was visible. In most of the shots on goal, the goal was very visible. And at some point, right after the shot on goal, or the goal, because shot on goal equals like anytime you shoot at the goal and in the goal. Every time there's been a shot on goal, there was like a close-up of Zlatan Ibrahimovic. So that was a very telltale sign. In fact, it was too telling. Obviously, it was not always Zlatan Ibrahimovic, but it was a little bit almost too telling, the fact that there was a switch in scenes. So we wanted to make sure we didn't just create like a scene change detector. And then also, we looked at player poses, so the way they were posing when they were shooting at goal. So armed with this knowledge, we now go into a phase called hypothesis-driven development, which is a fancy way of saying we're going to throw a lot of spaghetti at the wall and see what sticks. Basically, we're going to try out a lot of things, and if they get more than a certain percentage of accuracy or whatever we choose as the metric, we'll take that model and sort of like work more on that. So for this, we need some building blocks, because how do we actually take these ideas and turn them into features? So as far as machine learning building blocks, we have a couple. We have image classification. We know that we can absolutely figure out if something is a cat or not a cat. That is no longer even a difficult task in machine learning. It's like a commodity thing. So we could use this, for example, to figure out if there was a red card or a yellow card in the screen. We can also use things like object detection, so figuring out where in the picture we have a human, a ball, things like that. So that could be very useful for figuring out features like, if people were huddled together and things like that. We can also figure out the exact pixel level using segmentation, whether or not something like a specific set of pixels is a ball or a human or things like that. So in this case, we have, cars are classified separately, and the road is classified separately, and things like that. So we can use that to do background extraction. The next thing we can use is face detection. So if we wanted to detect Zlatan Ibrahimovic, we could absolutely do that. And it turns out, because that's also already sort of a solved problem, there is even pre-trained models that we can use for that only requires like one single picture of Zlatan or Messi or whoever we want to look at in order to detect them. And then we can also look at poses. So there's already pre-trained models and things for detecting joints, and we can take the joints and put them in as input features and understand, like, do we have a certain pose? Do we have certain gestures that happen, or maybe kicks, or things like that? So all of that is possible already with pre-trained models. And what was I going to say? So if you use, for example, OpenCV, a lot of these pre-trained models already even exist in there. And then we have a couple of non-machine learning things that we can use. So just to make things easier, we don't actually have to do segmentation in order, for example, to figure out whether or not we have cells that, in this case, this is a digital pathology slide that shows a slice of what could be a tumor, where the tumor cells have reacted with something, with a chemical that makes them pink. In this case, we don't actually need to do segmentation to figure these out. We can just do simple color decomposition. So what we do is basically say anything that's a certain range of colors, like RGB, you segment them out. And this is a very useful way to deal with things like this, where we don't actually want to do machine learning. We want to have very robust and sort of interpretable ways of understanding what we're picking out. So we can use this too, for example, for background extraction. So we use this temporarily in this project to figure out anything that was green, we removed it as field, for example. It didn't really work that well because it turned out like that a lot of videos had different colors of green, and there was too much other green stuff in the images to actually use the color decomposition to remove the greens. Then we can do other types of background extraction. So this is, how many of you use OpenCV? Okay, lots. Has anyone seen this with the background extraction? It's very useful. So we can do this. Let's see, I'm just going to show this file. So this is basically just CV2, create background subtractor, and then you just basically input a frame and it will do it. So what this does is it goes through your frames and it says what changed between the frames. So this is for if you have a stationary camera. Let's say you have like a camera in a shop or something, and you want to make sure you remove like the walls or the posters or things like that, and you focus only on the people in the front. You can use this background extractor. So it looks like this if you run it. And now this camera is moving a little bit, so it doesn't get like the really good effect like you would if you had a stationary camera. But you can see that it extracts the people as the white dot. So you can use this as a mask to just focus on the people. And And then we used optical flow. Does anyone know what optical flow is? No? A few people. So what optical flow does is basically it takes a few pixels, and you can focus and say that we're going to look at specific specific pixels. So we're going to, in our case, look at the extracted players, and then focus on and see how those pixels move between frames. So this is also an image processing thing. It's not a machine learning thing, but it looks like this when you apply it, and this is also from OpenCV. So in this case, it follows the lights and the mirrors of the cars. So we can now use this to featureize and tell us basically how fast did people move, what direction did they move. Like here it's shown as a picture, but it's actually sort of like speed and direction in the background. So, and finally, we used a very simple way of detecting scene changes. So what we did was we took like 20 random pixels and saw how much they changed between frames, and if they changed enough, because normally between frames you won't change like too much at all. So if they changed a lot, we said it was a scene change. So now we can go through and actually test out our ideas. The loud crowd, we simply extracted the audio features using a Python library called PyAudioAnalysis. There are plenty of libraries like this, but this extracts sort of like the pitch and how much sound there is and a couple of other things. And we discovered that between the shots and no shots, there was a definite difference in terms of what the sound levels and what certain pitch levels were. So this was a very telling way. So even with just this information, and just a model based on this. So this is a 2D or 1D CNN based on this, or actually a 2D. But we got something like 86% accuracy. We could find the shots very well compared to the attacks. And then we looked at how the players were grouped, and we tried to figure out like how can we actually represent grouping of players and like players stuck together in a good way. And the way we decided to do it was like this. We divided the screen up into certain different sections. So in actuality, it's like 100 different sections. And each one of these, we went in and used object detection, so a pre-trained model for object detection to detect the players and mark down whether or not they existed in one of these sections. So go through that, and then we did that for each frame, and this created sort of like a heat map where we could see people moving along the screen. So this heat map was quite interesting because it then shows if there's a lot of people stuck together, it was like a very white spot, and if it was less people stuck together, then it was a darker spot. So using this and sticking all the frames together, we now created an image that we could use as an input for a new CNN. This did not give us a very good result, so this did not turn out to be like a very useful feature, but it's something that can be used like sort of as a toolbox for other things. The next thing, actually before we go through, when you're using something like this, so we use a pre-trained model for object detection. It looks like this. It's a ResNet COCO-based model. So COCO is a Microsoft dataset for about 80 classes of different objects like people and balls and things like that. But one of the problems you have when you use a pre-trained model like this is that you're not controlling the data that this was trained with. You're not controlling the data or like anything about how this was trained. So you might run into some quite real problems like bias and things that exist in the data. So I'm sure if you're doing machine learning, you're all aware of this. Joel Bulwalmini's study on gender in face detection. So where she discovered that basically while a lot of the big companies had really good face detectors and gender detectors in terms of Total total accuracy, it turns out that they were very, very bad for darker-skinned women because the data that they used was simply not that representative of dark-skinned women. In fact, the data that was used as benchmark for most face detection up until like 2 years ago was labeled faces in the wild, which is based on whatever pictures showed up in Yahoo News between 2002 and 2004. So very much like whoever was in the news, male, pale, and stale. A lot of, I think George Washington was like 5% of the total data or something. So he's detected a whole lot. However, this has changed since this picture, because this was based on her study. They changed the benchmarking. So IBM came up with a much more diverse data set, and now everything is benchmarked against it. And all of these three have upped their game. I'm proud to say, because I work at Microsoft, and it now has a lot better accuracy for all different types of ethnicity, at least the ones that they tested on. The other thing that you might run into, so that's on face detection, but just on regular image classification, if you use pre-trained models, is something like this. If you have this picture and you run it through any kind of model, you'll probably get a result like this. Right? So what seems like a cricket game is not really a cricket game to all of these, because most of the data that this is trained on, which is ImageNet in this case, is highly based on US and European-centric images. So it just kind of disregards the whole sport that's like a huge sport for millions of people, right? So you need to be a little bit careful when you use pre-trained models, because you can't control the biases and the things that are included in them. Anyways, that was my soapbox about bias. If we go over to speed and direction, I've already talked a little bit about how we did that with focused optical flow. So we did the optical flow, but just based it first on bounding boxes for the players. And then we looked at player poses. So the optical flow was also not very successful. We looked at player poses, and with poses, we went and basically extracted the poses like this, again with a pre-trained model. However, what we noticed a lot when we tried to do the poses was that most of our players were very small and often in this direction. So it was not very easy for the machine learning models to even pick out like the poses of the players. So we scrapped that idea quite fast. And then we came into, I'm going to do a passes on red and yellow cards. So even though they are not shots on goal, we did a red and yellow card classifier. So for this, we created our own image classifier. And if you're not very in tune to how image classification works, I'm just going to give a quick 2-3 minute intro to image classification. So if you have two pictures, you have a picture of a chihuahua and a picture of a muffin, or lots of pictures of chihuahuas and lots of pictures of muffins, and you want to figure out which one is which. The way that image classification works and the neural networks for image classification works is like this. You bring in all your images, and then it has a number of different layers, all those dots in there. And in the first layer, it extracts some very, very simple features. So it extracts things like colors and small small patterns like dots or meshes or things like that. And then in the next layer, it puts these together to more advanced features. So now we might start looking into more complex patterns, or maybe eyes or noses and things like that. And eventually, when we've had enough layers, we have enough features that we can actually tell apart a chihuahua and a muffin. So in this case, I've only shown 2 layers, but normally you would at least have maybe 5 or something. And the more you have, the more complex features you can figure out. But the more you have, the more data you also need to have to not get like very specific features. So in CNN literature and things like that, you will look at it like this, in which case the first part is the one that extracts the features, and then once you have the features, you can then classify on top of them. So each one of these convolutions is essentially just a little filter. So if you can think of it like an Instagram filter or something like that, that picks out bevels, like edges and things like that, or it picks out certain colors and extracts those. A convolution is basically just actually a math operation. It's a multiplication between two matrices. But what it turns out to do is extract things like that by shining a little flashlight with a filter on top of the picture, and then marking red, no, yeah, and then marking down if it matches that pattern, if you will. And then you get to this point where you have the actual features in this dense layer, and then on top of that you have the classification. So just to show you how simple it is in Python terms, this is how a convolutional neural network looks in Keras. Keras is one of the main frameworks for doing deep learning in Python. So here's where you build up. You say we want one convolutional layer with 32 filters that are 3 by 3, and then max pooling. The max pooling layer, what it does is it compresses the result of the convolutions, so you don't end up with like super huge results. And then finally, in this flattened layer, this is where we create this feature set. And so we say we want like 512 features, and then a 1 or a 0. In this case, a 1 means Chihuahua, and a 0 means muffin, maybe. And then you just fit this and run this. And normally, even this doesn't take super long if you have just a small amount of data. Let's say you go through something like this with 500 or 1,000 images. It might take a couple of seconds on this type of machine for each epoch. Epoch means one pass through the data. If you want to go through and actually do this by yourself, I would definitely recommend this book if you haven't read it. It's like a majorly good book on deep learning in Python. So with that in mind, we decided, and I should say, the classification of the red and yellow cards, we did that on every sort of like 10th frame or so in each one of these clips, because you don't have to do classification in every frame. It's not likely that you're holding up a red card and then like you manage to stick it down between 2 frames. So we didn't need to do it on all frames, but we just did classification like that and could very, very accurately tell if a clip contained a red card or not. Now, going back to the shots on goal, we've tried out all these things where we featureized ourselves. So now we're actually going to go through two ways to do it sort of like end-to-end. One of them was using something called VGG embeddings. So if we look at this picture again, this part, like the actual features, this is the magic of deep learning. And this is sort of like, if you understand this, you understand deep learning completely, because this is what it all comes down to. So these features are called embeddings or intermediate representation, or maybe a secret code. And the way they work is like this. Let's say I'm going to recommend a book. I have a large number of books, and then I'm going to recommend a book either to my daughter or to my husband. And I want to figure out which one I should recommend to each. So I put them on a line like this, where these are children's books and these are adult books. And then I say, well, my daughter probably likes these, and my husband probably likes these. I can go in and add a few more dimensions. I can say, let's say, Maybe some of them are fiction and some of them are not fiction. And now I've sort of like given them an embedding is sort of like a more semantic meaning. And my embedding is now basically in the coordinate system how adult it is or how much fiction it is. So I can do this for a couple. And the closer something is together in this space, the more alike they are. So likely when you add, like when you create embeddings for cats and muffins, the cats will be close together here and the muffins will be close together here. And then you can just do a classification like to separate them. So we can go ahead and add more layers to this, so more features like do they have math references, or the US-centric, shit-lit, funny sci-fi lawyers with Brad Pitt like play a character in a movie. I mean, adding these is like weird things because it turns out we don't actually have to come up with all these features. The machine learning model will do that for us, and it will figure out what features are important for this particular picture or this particular video. And all this now turns into an embedding. And what we do with in this end-to-end scenario was we use a pre-trained model again, extract the embeddings for every single frame. So the embedding is now like 512 or 2000 or 1024 list of numbers in a 2024 coordinate system that represents that image a little bit better, like a little bit more semantically. And we put them together like this, sort of like in a matrix, and then we get these kind of images as output. So this is now quite interesting because each one of these lines, each one of these columns represents a feature. So we might have one that represents grass and one that represents whether or not there is a goal, or one might be representing, something completely different. But this is now useful input for a machine learning model. And if you look at this, you'll see that there is like a line right in the middle. This turns out to be a scene change. So this is like a complete split of where all the features suddenly changed between one frame and the next. So this is a very telltale sign that this is a scene change. So we use this, and this gave us like a huge increase over all the other models. I think now we're at like something like 90% accuracy on shot or not. However, this pre-processing and creating VGG embeddings was quite expensive. So it's not really useful in terms of like actually processing all the videos like this. And then we went through and we did another end-to-end, which is a 3D CNN. So looking at the CNN that we had before, but now in 3D. So we do this for images, but all the images stacked together like in a 5-second clip. And this turned out to actually be the best of the models. But one reason why we didn't go here immediately is because this is usually very, very expensive to train. Until we discovered that there already existed something we could use. So if we look at something like determining whether or not it's a chihuahua or a muffin, when you look at a picture like this, you don't actually need to maybe know exactly what a chihuahua looks like and exactly what makes a chihuahua different to a chinchilla or something like that. The only thing you need to know is sort of like that chihuahua is a dog. Like you can use a lot of your past experience to understand which one is a chihuahua and a muffin. So you can use your past experience of all the dogs you've seen and all the baked goods you've seen, right? Similarly, we could use this for our training, and this is called transfer learning. So the way this actually works is you use a model that someone else created on a huge data set, in this case the kinetics data set, which is gestures and things, and we simply remove the classifier, so we get to the embedding part of the video in this case, and then just add our own classifier. So in this case, we would add shot or not shot. And this now took us to, I think we're at this point at like 94% or something, which is a major achievement for for video action detection, actually. So what did it actually learn? Because one thing we're worried about is sort of like, do we learn a lot about Zlatan Ibrahimovic? Is he like are we just creating a Zlatan recognizer? Because we don't want to do that. So we need to figure out a way to interpret this and determine that we're actually learning the right things. Some other things we were worried about learning was a goal detector, because we also didn't want it to match, we didn't want it to say it was a shot on goal just because the goal was in sight. Some other things we were a little bit worried about was, were we creating something that could only detect, for example, people wearing red, or maybe we couldn't detect sort of like shots on goal in videos that were not UEFA League videos. So you want to make sure that your data is very representative of the actual input data you're going to get later, so that you don't end up just creating like something that has very good accuracy for George Bush. And some other things, and these come from a little bit different projects, is we had a project a while back where we were detecting shoplifting. And in that case, we have a very consequential decision in terms of like, if we're saying that someone is shoplifting, that's quite a bad statement. So in that case, we don't want to do prediction, for example, prediction saying that yes, because you're a man between 20 and 40 wearing a hoodie, because those were the ones who were most often present, that doesn't mean you're a shoplifter. So in that case, we need to do things like try to remove all the preconceived biases and try to do detection, not prediction. And then finally, in some cases, also from the shoplifting case, for example, we don't want to go in and detect things like the background or the posters, or let's say, for example, in shoplifting training, let's say all the shoplifting cases were done during Christmas. We don't want to create like a Santa detector and say that as soon as we see like, I don't know, Christmas specials in the background, we're assuming that someone is shoplifting, things like that. So in that case, we need to remove the background. So what we did for this case was we created something where we imprinted on the video when it was a shot on goal. So the end result looks like this. Let me move to where the interesting part. Okay, so now, see, they're going in, shooting on goal. So this green bar here shows you when it gets interesting or not. So blue means not interesting. Now it's getting interesting. And then people have stopped. So we use this to do visual inspection. I think this is pretty darn cool, actually. And the last thing I want to leave you with is that no matter what you're doing, you need to make sure you handle the cases where things go wrong. So no matter if you have like a 99% model, you will get things like this. So this is China, where they use face detection along with looking at like the zebra crossing to figure out if someone is jaywalking or not, and then automatically sending them fines. Which, I mean, it kind of sounds a little bit dubious, but it seemed to work until this happened. So this woman who was on the bus was getting a whole lot of this will happen. So what you need to make sure of when you create a model, independently of what you're creating, is that you have some kind of like checks and bounds and some kind of way to get out of when things go wrong. So adding a human in the loop, someone that for a while, or depending on the severity of your decisions, forever, that goes through and actually figures, like says yes or no. So in our case, what we did was, in the end, like actually, we're going to have this for about like at least half a year, or until we feel that the model is working. We're going to have people that go through the actual results and create the final videos for us. So just use this to automate the markings, but the final videos will still be overseen and created by actual humans for a while. And throughout all of this, I wanted to just leave you with one thought, and that's when you're faced with a problem, no matter how hard or how big or how difficult it can be, try to separate it down into the smallest part. Try to sort of like break it into edible chunks. So keep it simple, because the older I get, the more I realize the biggest problem to solve in tech is to get people to not make things so complicated. And with that, thank you so much for having me.
So thanks a lot for Tess. We have 1 minute left. I guess we can take one question.
Hi, thanks for a great talk.
Thanks.
So you mentioned a lot that you wanted this to work for all kinds of videos. So how did it actually perform compared for, like, say, a parent just for a parent just recording their kid's video game from the sideline compared to having professional video systems?
So we haven't actually tested it yet on like non-professional videos, but we've tested it a lot on things that were not like major league. And it seems to be working quite well, actually. It turns out that like transfer learning on top of kinetics is quite powerful and picks out like a lot of the good features, if you will. So it worked out very well. Not as well as on the original games, but yeah. But that's also something that now, so right now we're doing it for the major league, and then as it's moving to smaller leagues, it will have to be retrained also on those. Because right now we don't have any training material for them. Thanks.
Okay. Thank you, Tess. So
I'll be around.
If you have more questions, you can take it with her during the coffee break in 30 minutes.
Yeah.
So big hands.
Thanks.